So this evening's presentation is the Big Bang and the formation of the universe. This was a very difficult topic, I will tell you, to try to put together, because to understand not only the Big Bang, but the formation of the universe, you have to kind of understand some very elementary, I'll call it physics. I'm going to try to be very slow and careful about walking through all of this. I try to get it as simplistic as possible, but not to the point where it's not correct, let me say. So let me first start with the big picture. This funnel, by the way, is on the far left, the beginning of the universe. This is a picture that you'll see throughout this presentation, but it's also one that you'll see on the web. This was done by NASA. It's sort of representation on the far left of the beginning of the universe, the so-called Big Bang, and going to the far right, 13.7 billion years to the present. So as far as the big picture, what I'll be talking about is initially the universe started as a very dense, very hot point. And at some point, that particular initial part of the universe contained, and I'm going to explain this later, something called a superforce, which is made up of four forces. I'll go into this more detail later. So this is at the very initial stage when the universe began, at least as far as we know. These forces I'll be talking about then separated. One of the forces, for example, is gravity, that we all know and experience. Then the universe all of a sudden expanded 100 million trillion times at that point. There wasn't an explosion. I'll be talking about the term Big Bang and unfortunately sort of the connotation that it has given people, but it wasn't like some big explosion. But we'll talk more about that later. So all of a sudden, the universe expanded just tremendously. We're talking about within a fractions of a second. Then, and this is very important, hydrogen was formed. The very first atom was formed, again, in the very early universe. At some point, light appears. Up to that point, the universe was dark. All of a sudden, 380,000 years after the universe began, there was light. And you'll hear me talking later about why we know that, because at that point in time, 380,000 years after the universe began, there was an imprint that we can now see back in time to that point when that happened. Now, again, I'll talk more about that later. And that's that sort of multicolored thing you see there. Then things really started taking off. Stars were formed, star clusters were formed, galaxies were formed. And then something strange happened. All of a sudden, the universe started accelerating very quickly because of something called dark energy. We'll talk about that later. And finally, we're at the present. So this is just a very rough, big picture idea. I'm going to go into more detail, mostly actually at the very beginning, because that's sort of the most interesting part when things really sort of got going. So let me just sort of cover the following topics then. I'm going to first give a little historical perspective of how the term Big Bang came about, as well as the different theories about the universe, whether it was static all the time, whether it was expanding. I'm going to talk about three things that are sort of fundamental to understand how matter was created, how the universe then got going, how it got to the present day that we see now. And we're then going to talk about all the way to the present. One of the things I think that people find a little hard to grasp, especially since James Webb was launched and we hear things like James Webb is able to look back in time, billions of years. How is that even possible? So we'll talk about that concept, which I call our time machines, the ability to look back, so-called, in time. And finally, we'll talk about some of the unanswered questions. There's probably more unanswered questions than our answers that we know about. So we'll say a little bit about that. Okay, so let's talk about historical perspective. The first thing I just want to point out is there have been three evolving theories about the size of the universe. The initial theory was that the size was static. The universe was there at the beginning, all the way to the end. Nothing has changed in terms of size. Folks then realized that the universe was really expanding. And then folks realized not only was it expanding, but accelerating. So the theory and the concepts about the size of the universe went from the standpoint of it's there, it's always been there, always the same size, to it's expanding, to it's accelerating. These are three different theories, if you will, about the size of the universe. So one interesting thing I just want to say from a historical point of view, something called Einstein's biggest blunder. In 1917, when Einstein put together his general theory of relativity, his theory inherently predicted an expanding universe. But at the time, the leading theory was the universe was static. So Einstein thought, well, my theory can't be right. I need to introduce a fudge factor, which he did. It was called lambda. So he introduced this fudge factor called lambda. Well, lo and behold, in 1929, Edwin Hubble discovered that indeed the universe was expanding. At that point, Einstein said this was the biggest blunder he ever made, was to put that fudge factor in, because his theory actually did predict that the universe was expanding. Now, where did the term Big Bang come from? In 1949, there were two competing theories about how the universe began. One was that it started from a single hot, dense point, which is what we believe today was the beginning point. The other theory was that there was no beginning. It was continually created. It was continuously there. Matter was created, but it was just always there. In a March 1949 BBC radio broadcast, a British astronomer named Fred Hoyle, who was a proponent of the second theory, namely that the universe was always there was no beginning, there was no end, used the term Big Bang, not in a pejorative way. He was just trying to describe the competing theory. He said it's like there was an explosion, like a Big Bang. And that's where the term Big Bang came from. Unfortunately, that name has stuck. And as we'll see, it's not that the universe all of a sudden exploded. We'll see how things evolved in different steps. But that's where the term Big Bang came from, and we still refer to it as the Big Bang. So when we hear and talk about Big Bang here, we're talking about the beginning phases of the universe. So how do we know what we think we know? From physics as we know it, we're going to see a little bit later that some of the things that we're discovering are questioning the current physics that we think we know, as well as just theory, mathematical theory, physics theory, and so on. Computer simulations. So large computers at NASA and elsewhere are able to churn through and kind of rewind back to billions of years what things should have been to get us to the present configuration. So a lot of computer simulations. And we'll see also with some of our telescopes, especially more recently Hubble and James Webb, doing observations that confirm some of our theory and some of our simulations. So these are ways in which astronomers have come to believe what we think we know about the universe. But we'll see that there are many, many things that we don't know. And there are things that may change our theories about the universe. Okay, so I'm going to talk about the formation of the universe as a story. I'm going to talk about the early characters in our story. These are quarks, electrons, and unified force. You don't have to worry about remembering, the details of what I'm going to be talking about here. You get a general sense as we go through the story of how these characters in the story all fit together. Chapter 1 of our story is that there was a unified force of 4 major forces: gravity. We'll talk about the next 3 in a little bit: the strong force, electromagnetism, and weak force. Again, don't worry about remembering that each of these forces. I think it'll become clear later. These forces helped the early characters in our story, quarks and electrons, to come together to create protons and neutrons, 2 other characters in our story. The protons and neutrons merged to form one of the major characters in the story of the universe, hydrogen. Hydrogen came together to form helium. So the story of the universe is one where we have some very initial particles coming together via different forces to start forming the very elementary atoms in our universe, hydrogen and helium. We're going to go through in a minute some of this more detail. Chapter 3 of our story is all of a sudden light entered the picture. Chapter 4, things really took off. Stars formed, galaxies formed, and we now are where we are today. So these are sort of what I'll call the 5 chapters in our story about how the universe formed. I'm going to talk about each chapter in a minute. Now, behind the scenes, there's some mysterious characters in our story that we don't know much about, but played a major role, called dark matter and dark energy. These are mysterious because we don't know really much about them, but we see their effects on galaxies and the rest of the universe. So these are, again, very mysterious, but we believe they're real. Now, what we don't know is what happened before chapter 1. And we don't know how the story is going to end. And there's different theories about each of those. So I'm not going to go into before, and I'm not going to go into after. All of you can form your own judgments about those. So we're going to begin at really the initial story of the universe. But before that, I mentioned these early characters I talked about, the quarks and electrons and that sort of thing. Just want to say a few words about those. The most fundamental, or one of the most fundamental particles that created all of matter are called quarks. 3 quarks together form a proton. A proton is a basic element. As you see, the plus sign has a positive charge. So we have protons that have a positive charge. Protons can be linked together. So we have 2 protons that are tied together via one of the forces. We'll see in a minute, the strong force. So these protons have positive charges. There are other parts of the atom that have no charge. They're neutral. They're called neutrons. And so we have neutrons that are tied together with protons. And then we see electrons entering the picture. So this is sort of the classic picture, if you recall, in high school and science classes, where you see electrons orbiting protons and neutrons. This is the atom nucleus. In fact, what you're seeing is the helium atom. Now, let me just say a few words about this picture of electrons orbiting. We have found that with quantum mechanics, this isn't really the correct picture. Electrons aren't orbiting like we learned in high school or middle school. They're not really orbiting like you're seeing here and like we've seen pictures before. from a quantum mechanics point of view, electrons are really in a number of different positions simultaneously. It's kind of really weird, and try to understand that. But an example might be a coin that is spinning. It's not up and it's not down. And in fact, we don't know whether it's going to land on heads or tails until we smash it and it lands. So until we measure it, we finally know where it is. And that's the same with electrons. They're in the state of maybe here, maybe there, but when we measure it, all of a sudden it collapses into, this is where it is. So it's a weird world of quantum mechanics. So it's not that electrons are orbiting atoms like you see it here, but that's just an aside I just want to kind of point out. So this is the atom. Now the forces. Well, we know gravity, right? Newton with the apple falling down discovered gravity. We all experience gravity. Within the atom itself are the other three forces. So this is again our little atom here. The strong force is what ties these quarks together. Okay, so we have the strong forces tying the quarks together that form the protons and the neutrons. The strong force also ties the protons and neutrons together. So the strong force is tying everything together within the atom. If you can think of magnets, right, there's positive and negative parts of a magnet that attract each other. So the electromagnetic force is the force that's pulling together the negative charged electrons and the positive charged protons. That's the electromagnetic force. And the last force, which we'll talk about later, is the weak force. This helps transform a proton into a neutron. So again, not to get into the details for you to know, except that there are four forces and there are these elements that make up atoms. Atoms, of course, come together and make up molecules that make up the rest of the matter that we see. The interesting thing is that we would, as humans, think that gravity is the strongest because that's what we experience. Well, it turns out gravity is the weakest of all these forces. The strongest force is the strong force tying the protons together with the neutrons and the quarks together. The electromagnetic force is the next one, weak force, the next, finally gravity last. I'm going over all of this because when we start stepping through the formation of the universe, you're going to see how all of these start coming together. Okay? Let me stop there and see if there's any questions. Kristen.
Times there can seem as different, but that they might all be aspects of the same force.
At the very beginning, yes, they were part of this super force. But we're going to see in a minute that they started splitting off and became separate. But you're correct. At one point, and physicists don't know why that was or how that happened. But another point to make is physicists have found that the last three forces, strong, electromagnetic, and weak force, there's a general theory that ties all of them together. They haven't found yet a theory that ties gravity to those. Maybe that's what you're referring to. There's yet to be found a theory that ties all four forces together. So whoever does that is going to get, I'm sure, a Nobel Prize. But that is speculation that there is some grand theory that ties all the forces together. Okay. So in the very early part of the universe, we had the hydrogen atom. We're going to see how that evolved. And it's very simply one proton, I'm designating a blue with a plus, and one electron. The simplest thing you could do. By the way, nature likes everything being neutral. So atoms, if they have two protons, nature likes them to have two electrons to balance out the charge. So here we have one proton, one electron. Nature likes that. Everything's neutral. Plus and minus together is zero. The next early atom is helium, which is what we saw before. 2 protons, 2 neutrons, 2 electrons. So the 2 protons, positive charges, are offset by the 2 negative charges, electrons. So these are the early atoms in the universe. Now, one of the things that we're going to see that drives the formation of energy out of stars, and in fact drives nuclear reactions in our nuclear reactors, that drives, unfortunately, nuclear bombs, is the coming together of hydrogen to form helium, because there's energy that's released in that. And we'll talk about that. So let's say I have 6 hydrogen atoms. They're all, again, just each has a positive proton. These 6 hydrogen atoms in the early universe, they were compressed together, gravity compressed hydrogen gas together under extreme heat and pressure. And the weak force, this is where the weak force I mentioned earlier comes into play, changes these protons that you see the little plus into a neutron. This resulted in 2 hydrogen atoms and helium. Now, if you count the blue pluses, you've got 6 on the left, you've got 4 on the right, and you've got 2 neutrons. So somehow 2 of the hydrogen atoms turned into neutrons. Okay. In that process of doing that, there was energy that was released, because those 4 hydrogen atoms and helium, there's mass that has been lost in that. And that loss of mass creates energy. Our old buddy Einstein equals mc squared equates mass and energy together. So mass can be energy, energy can be mass. So in the process of going from the red box on the left to the right box on the right, energy is released. And that is what powers our sun, what powers the stars, as I said, even what powers nuclear weapons. Now, notice something interesting here. On the left, we have 6 hydrogen things. On the right, we only have 2 left, and we have helium. This process keeps continuing, but what's happening is hydrogen is getting lost. It's turning into helium. So this is how stars start dying. The hydrogen is turning into helium. There's less and less hydrogen. There's greater and greater helium. And our stars, even though they're shining, eventually then die because we lose hydrogen. So this process of what's called fusion of hydrogen into helium is what in the early universe created from very fundamental atom of hydrogen, created the next particle, helium. And then from there, other particles of greater complexity were created. So I wanted to just give you a sense of, in the very early universe, this process was so critical to getting things going. And even today, in our world, we see its use because this is how nuclear reactors work. Hydrogen fusion into helium, energy is released, and that's how, again, our nuclear reactors work. So let me just stop there and see if there's any questions. Again, just kind of not to remember any of the details, except just the big picture that hydrogen is important at the very beginning of helium. Yes?
What's the difference between fusion and fission?
Very good question. Okay. In fact, I have a slide on that. Fission, I'll just talk about it. Fusion is bringing together hydrogen to create helium. Fission is splitting of the atom. If you remember, those of us who grew up during the earlier nuclear age, we would hear the atom was split. So fission is basically splitting the atom as opposed to fusing it together. And that is what causes also energy to be released. So the very early atomic bomb went out, that happened in Hiroshima, for example, was fission. In today's nuclear weapons, fission actually takes place first to cause fusion to happen. So in today's nuclear weapons, this fission happens that then causes fusion to create more energy. That's why today's nuclear weapons are even more powerful than the ones, for example, at Hiroshima.
So this on the screen here is fusion.
This is fusion, right? Let me,
And we have yet to create this as an energy source.
yes, very good point. Very good point. The thing that would be phenomenal if we're able to create, I'll say it in a large way, in a controlled environment, fusion from hydrogen, because that would be, for example, the equivalent of taking water and converting water into energy. So the golden thing that everybody's looking to try to do is to create a fusion reactor to create power. That would be the ultimate advantage to us in terms of energy savings. So yes, fusion,
Reactors today, fission.
yes,
It's ready, the
splitting of the atom would be fission.
splitting.
Right. Okay. Any other questions? Okay. All right. So what I've talked about is protons and neutrons, things that we kind of know and can measure and that sort of thing. As I said, helium is created, heavier elements are then created as supernova take place, and we're all made, as we've said before, of star stuff, which is, atoms, more complicated than helium, for example, and hydrogen. And this is what makes us up and everything we can touch and feel. All of that is what we call ordinary matter. Okay, stuff we can touch and feel that's made of atoms that make up molecules and so on. But we do believe that there's matter out there we can't explain that is holding the galaxies together kind of as a so-called gravitational glue. We call this dark matter. Unlike ordinary matter, we can't see it. So we believe it's there because of the effects that it has. And again, that's all we can do is observe its influence. So we have ordinary matter that we can touch and feel. We have this mysterious thing out there called dark matter. And then we have another force called dark energy that is, again, something that we haven't seen. We see the effects of it because we see that the universe is accelerating. The only way we can explain the universe is accelerating is because there's some mysterious dark energy out there. So we have dark energy, dark matter, and we have ordinary matter. Now, as we said, that energy and matter kind of are interchangeable. So if we take a look at the combination of ordinary matter, dark energy, turns out ordinary matter that we can touch and feel only makes up 5% of the universe. Everything else out there, 95%, we have no clue what it is. So let that sink in for a while. So, and again, dark matter and dark energy, we again just know from the influence that they have on everything out there. Okay, let's talk about light. So one of the elementary particles is, I'm sure heard of, called photons. This is what carries light. They're created when an atom's electron releases energy. Now, the redder the color of light, the longer the wavelength. So for example, if I look at a rainbow of colors, blue has a certain wavelength, but as light is stretched longer wavelength, it gets redder and then it gets into the infrared. We, with our eyes, of course, can only see up to red. There are some animals that can actually see in the infrared. We have some telescopes now, like James Webb, that can see in the infrared. Most of the telescopes that we've known before have been able to look from the blue, let's say, into the red. So we've been able to now look into longer and longer wavelengths. And you can see why that's important, because this is what helps us accomplish our time machines. In fact, further in the wavelength of the electromagnetic spectrum is microwave. We're going to see an instance of where microwave comes to play. So this is light. We all know, we all kind of get an idea of what light is, the fact that, different colors of the rainbow, but just keep in mind that each color has a different wavelength, sort of stretching the wavelength of light. Where's what? I'm sorry. Right. So imagine a train whistle. Okay, so you're next to a train whistle, and well, let me not use that example. Imagine an ocean. So it's got a certain wave. Okay, and there's certain energy with those waves. Let's say the ocean, the waves get longer and longer. Okay, and so imagine that's what light is. Imagine light is on one end, it can be very wavy when it's blue light, and then when it's kind of the waves aren't quite together, it becomes green light, and so on. I don't know if that answered the question.
Got it. So if that comes to the release, then.
Yeah, so one of the interesting things about light is it's both, and this really gets strange now also, is both particles and waves at the same time, which is a whole nother strange thing. So even though I say it's carried by photons, it actually is like a wave as well. And again, we can spend an hour on that, but it's both a wave and particle at the same time. Maybe that's what you were thinking of. Okay. All right. So just to recap, quarks are the most fundamental particle. Protons and neutrons are made up of quarks. Nature likes stability. They like, nature likes plus and minus to neutralize out. Strong force brings quarks together. Electromagnetic force brings positive and negatives together. The weak force, we'll see, as we saw in that fusion thing, will transform a proton into a neutron. Gravity acts between masses, and dark energy is some invisible force. And finally, light is carried by protons. The redder the light, the longer the wavelength. All of this, what I just talked about, is leading into especially the early phases of the universe, because you'll see how all of these now sort of come together. So let's talk about the timeline. In the very first second, the universe, first of all, we believe started, again, as an extremely hot, dense point containing all of these four forces I mentioned unified together. They're all like one force. Physics and physicists can't explain that, but they believe that was the case. So we have this initial point in time. Again, I'm not going to talk about before, because I don't know what happened before. I don't think anybody really knows what happened before. But let's just say some initial point, and then things started taking off. In the millionth of a trillionth of a second, gravity separated from the other forces. So gravity splits off from this super force we talked about. And then in the next zillionth of a second, the universe expanded 100 million trillion times from one point. In the next zillionth of a second, the strong force separated. Then the electromagnetic and weak force separated. So now all these forces we talked about have separated out. And now these forces are able to bring together quarks. We'll see in a minute. Photons and electrons formed, and the quarks are bound together, and protons and neutrons are created. So in the first 0.00001 seconds is when the first parts of an atom, protons and neutrons, were formed. Now let's jump from 1 second to 380,000 years after the universe began. In the first second, photons were, that was the dominant thing. They were just sort of floating around. But electrons were prohibiting photons from traveling. So the universe is very dark. This is called the dark age. Photons are there, but they're being captured by electrons, so there's not any light. Protons and neutrons fuse together to form hydrogen. And when that happened, the protons captured these free electrons, and all of a sudden now light was able to happen. So the fact that these protons captured the electrons, which were keeping the photons from creating light, all of a sudden now light happened. And that point in time, 380,000 years after the universe began, we see evidence of that because we look back in time and we see what's called the cosmic microwave background. The light that started 380,000 years after the Big Bang has come toward us now and has moved into the microwave. And I'm going to talk about how that happens in a minute. So yes.
0.00001 second, so, I mean, is there evidence?
It's theory,
Okay.
computer simulations. I mean,
It's so exact, you have to.
I've looked at multiple sources and I keep getting the same number. So I can't explain it, but I'm sure, Joan.
You're not talking about the sun. Is not.
Right, good point. Good, very good point. The light is just imagine that, imagine your light polluted sky. It's the best way I could explain it, is photons were just there. I mean, it's not that they were created. You're right. There was no stars to create it. It was photons that are the result of stars' energy, but there were photons there in the initial universe that were just there. But not created, you're right, not created by stars, because there were no stars yet at that point.
So they were low, photons were low.
Yes, yeah. And the cosmic microwave background is sort of a imprint of that, but as that light moved back, as we have moved forward in time, that's now in the microwave range. Okay, then to the present, 150 million years after the Big Bang happened to 1 billion years, gravity compressed gas, first stars were born. These were huge stars, 30 to 300 times as big as our sun. Star clusters then merged into galaxies. This is about the time, by the way, when the Milky Way galaxy was formed and when our solar system was formed. And then about 9.8 billion years after the Big Bang, this dark energy all of a sudden came to be and overcame gravity to the point the universe then started accelerating. Nobody knows why. But there's just evidence that that's when it happened. So today, dark energy is continuing to accelerate the universe. So just to recap, going back to our original picture, again, the universe started as a very dense early point, very hot. All four forces were in a single force. They started separating. The universe expanded. Again, in the zillionth of a second, all of this happened. Hydrogen is formed, light appears, and we see that as its cosmic microwave background. Stars are formed, star clusters, galaxies, dark energy came into being, universe started accelerating, and here we are today. Okay, so imagine you're in a car. Imagine you're at a stoplight. So you're just static. You're not going anywhere. So that's static. Okay, now imagine you're on speed control at 55 miles an hour. So you're going at the same rate, 55 miles an hour. Okay, so that's expanding. Now imagine you put your foot continually on the accelerator, going faster and faster and faster and faster. That's accelerating. So expanding, when I talk about expanding, it's as if the universe size is increasing at a constant rate. Your foot's on the accelerator, but always at the same place. But now as you start putting your foot more and more and more and more, it's accelerating. So we talk about static if you're at a stoplight, expanding if you've got your foot always at 55 miles an hour, and accelerating if you're continually going up. So, I'm sorry? New matter is always being formed, yes. But when we say that dark energy is accelerating the universe, it's as if it went from 55 miles per hour, all of a sudden the accelerator is going faster, 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 faster. And we don't know if it's going to stop. Maybe the foot comes off the gas pedal, we don't know. But right now it's going faster, faster. John.
Where do you know? So when you say it's dating, I was not that the universe itself is faster and faster, just going into what if it's nothing.
So imagine a balloon, and you got let's say 2 points on the balloon, okay, and you start blowing up the balloon, let's say at a constant rate. It's sort of going like that. But now let's say you really start just giving it more and more air, all of a sudden it starts really going faster, faster, faster. So it starts, the size of the balloon starts getting bigger and bigger, much faster, faster, faster. Does that make sense?
What you're talking about is, I always thought the universe is going into nothingness. So there is nothing, but it's getting bigger. It's the universe itself is getting bigger.
Yeah, I can't explain your answer. I don't know, and I don't know, Mark, do you know?
Yeah, that's the question. The extent, that's a really difficult question. One way I think of it, we don't know if this is true or not. The pretend universe is infinite. Then you can imagine expansion in space. If we're all galaxies, suddenly, 100 years we're all places far away. 200 years, so that's the way it's expansion. Now, the universe might not be infinite in some ways, then you discuss because, and we don't really have a creating so far because you're imagining that getting outside of the universe, but there's nothing that's noise.
Does that mean more and more dark energy relative to other things?
Yeah, that's what's happening because as you expand, matter gets spread out. We think dark energy is a property of space, and it doesn't get spread out. That's why later the universe becomes more important. The early ones
Okay, all right, thank you. All right, so how are we able to look back in time? Okay, so I tried many different ways to explain this, but bear with me. This is my explanation. Imagine Malcolm has a lady friend, Jane, and let's say Malcolm throws a bottle every day into the ocean. Assume it's a perfect ocean. There's waves, there's no hurricanes or anything, it's a perfect ocean. When Malcolm puts a message in the bottle, that bottle gets to Jane just perfectly fine. So Jane is getting these messages in the bottle from Malcolm. Okay, everybody with me so far? Right. Now, let's suppose that as soon as Malcolm throws the 100th bottle in, something unfortunately happens to Malcolm. Poor Malcolm. So he throws the 100th bottle in, and then Malcolm goes away. Jane is still getting these bottles. And she's thinking, wow, Malcolm's still sending me messages. I'm still getting messages from Malcolm. Until she doesn't get the 101st bottle, then she's thinking, gee, I wonder what happened to Malcolm. But up to that point, Malcolm's been long gone. She's still getting messages from Malcolm. Now, replace the message with photons, packets of light of Malcolm. Let's say photons that represent Malcolm. So, Malcolm's photons are coming to Jane. And again, Malcolm's gone away. She's still getting these photons from Malcolm. Malcolm's long gone. So again, she thinks everything's fine. So Jane would think that she's still viewing Malcolm, even though he's long gone. Now substitute a telescope for Jane and stars and galaxies for Malcolm. And let's see what happens. Well, we're going to see this is how we're able to see the early part of the universe, because light from stars and galaxies, the early part of the universe, that when light occurred, remember we said, now eons later are reaching us, even though this long gone, are now reaching us. So that's how we are able to see back in time. Just like Jane was able to think she saw Malcolm, she was seeing basically photons of Malcolm. The other thing I want to talk about is we said that the universe is expanding. And so imagine 2 points, A and B, and imagine that there's blue stars at B, pretty close to A. So the wavelength we see gets to A, and A sees blue stars. What's happening is not that A and B themselves are moving away, it's that the universe is stretching. So again, imagine a balloon, A and B on a balloon. A and B points are still there, but the balloon is stretching. So as A and B are stretching apart, when the blue stars at B start getting to A, the wavelength starts stretching. So it goes from blue to green to yellow to red, and then into the infrared. So as the universe has expanded, the blue stars that started out at B now arrive at A in the infrared. And so this is how James Webb, for example, if in the early universe we had blue stars, as those blue stars, as the universe has stretched over time, when they arrive at James Webb, they're in the infrared. This is why James Webb was created, to specifically look in the infrared, to be able to detect what was happening in the early universe. So this is our time machine, so to speak. The amount of shifting that has occurred gives us an indication of the distance and the age of when the photons that we're seeing happened. So this is how we're able to tell how far away something was in the age. Yes?
So, if we are now able to look back 13 billion years plus or minus at stars that were sending out light, right, at the speed of light, does that suggest that the universe expanded faster than the speed of light so that we could be way out here and see stars that go way back there? I mean, how does that whole thing? You see what I'm saying?
Rephrase it again. I'm sorry, I'm missing it.
Well, if we're seeing stars now that were born at the early stages of the universe.
Right.
And light travels at the speed of
186,000 miles a second, right?
yeah. And we're way out here. How did we get here before the light reached us? Does that? See what I'm saying? I mean, we would have had to be traveling faster than the speed of light to get ahead of that.
I think I'm getting you, but let me try it this way. The universe is stretching and the wavelength of the light is stretching. So the stars, maybe I'm still not getting your question. I'm sorry. Yeah, go ahead.
And we can only see the universe as far out away from us as it is taken light to get near to us. And so we see like a sphere around us, and from our observations, we look like a sphere. So it's not that we're suddenly seeing these stars from what was it, millions of years ago. It's that we're now getting that light because it's been that length of time to see light travel with us. That's it's like.
Yeah, but how did we get so far away from that light source that we're here seeing that light come at us? You know what I'm saying?
I get it. It's like he's saying, we tried, why is it taking so long for the light? How did we get so far ahead of the light?
Universe is stretching.
I think that the feelings, we all love at the same time, or we all love in the same place. Is that?
Or how did we go faster
How
than
do
the
we get
light?
way out here?
And now the light is now
Catching
getting
up to
catching up
reveal.
to it.
Well, one thing I'll say is, Dennis was describing, when in his history, talking about that super fast expansion of the universe. So that's when the
Oh,
universe became huge, really fast.
oh.
And so that's why, we don't know how big the universe is, I said before, but we know it's much bigger than the area we can see. So that galaxy just happens to be that far away, and it got there and then
In the like the 0.0
yeah, but that's
three
much
seconds.
way faster. We can actually experiment this. And it's happening.
Wait, say that again.
It's okay for two things to expand fast. It happens in
The universe or things can expand.
yeah, because the expansion is just like it's stretching. So if I go far away, I'm stretching twice as fast. And you know, if it's far away, so I'm expanding this to be really.
Oh,
And that's a little bit of what I'm saying.
Well, why don't we move on, but maybe if we have time after, we can huddle and go over these. Yes, one. I'm sorry? Well, no, the wavelength will keep getting longer and longer. So for example, the light that originally happened is now beyond infrared, it's in the microwave. So that's just gotten stretched into the microwave. So what we see is the imprint in the microwave of that early light 380,000 years after the universe began. That's evidence of, so it's just getting, yeah, and longer wavelengths.
And we're not looking at one particular spot in the sky.
It's the whole
We're
sky.
looking at the whole
Yeah, right,
cosmos.
right,
Yeah.
right. Now, we're going to see in a minute some interesting things about this, so bear with me, because it even gets a little even further weird. So here's an example of, in fact, this is rather recently, this is James Webb seeing an image of this galaxy that appeared more than 13 billion years ago only 280 million years after the universe began. So here's James Webb seeing in the infrared something that happened 13 billion years ago. Okay, this is, again, example of James Webb being this time machine. This, in fact, is the furthest galaxy detected so far. Now, an interesting thing has been happening recently. It's called the Hubble tension for this reason. In 1929, when Edwin Hubble discovered the universe was expanding, he defined the rate of expansion that called obviously Hubble constant. Okay, so this Hubble constant was so many, I'll just say it in simple terms, so many kilometers per hour that is expanding. Okay, or sorry, how much? Yeah, let me just leave it at that. What's happened is that with our modern technology, when we look back at the cosmic microwave background, what we'll call the dawn of time, we get one value for H. We get one value for this expansion rate. When we look at the universe currently, we get a different value. And this has been tried over and over again. And you get one value if you look back in time, you get one value of the expanding universe if you look at it now. This is called the Hubble tension because it's like, what's going on here, And the thing is, if both are accurate, then that says something happened that altered the expansion rate. It was one thing if we look back in the universe, it's one thing that we look at now, something may have happened. So this is currently the thing that cosmologists are trying to figure out is this for real? Are these really differences in this value of this expansion rate? Because if there is, then that says something has happened that we're still trying to explain. Okay, so just to wrap up, what are some unanswered questions? Well, one is, what was before this initial state of the universe? I don't know. This super force that was at the beginning, when all the four forces were united, what was that? As I said, as Kristen sort of pointed out, we don't yet have a unified theory of how all four of these forces currently play with each other, even existed initially. What caused the universe to change from its initial state? It was this hot, dense point. All of a sudden, things started happening. What started that? What is dark matter? What's dark energy? How are we going to resolve this Hubble tension? Okay, these are some key things that folks still are trying to figure out. Will the universe continue to accelerate, or will it slow down, or in fact, will it collapse? So these are the unanswered questions, and some of them are sort of interconnected, but who knows when they will be resolved. So that's it. And if there's any questions.